Welcome to G Fun Facts Online. Today we are diving deep into an engineering marvel that challenges the very foundation of aerospace material science. When we think of space travel, we visualize titanium alloys, carbon fiber composites, and gold-plated mylar thermal blankets. These are the materials of the future, designed to withstand the harshest environment known to physics. But on November 5, 2024, a SpaceX Falcon 9 rocket launched a payload that disrupts this narrative entirely. Tucked inside the Dragon cargo capsule was a tiny cube, measuring just 10 centimeters on each side, made not of high-grade metal, but of wood. This is LignoSat, the world's first wooden satellite, built from hinoki, a Japanese magnolia wood traditionally used to craft the sheaths of samurai swords. This is not a gimmick or a publicity stunt. LignoSat represents a serious, scientifically rigorous response to a looming environmental crisis in low Earth orbit. To understand why a team from Kyoto University would bet on a material that predates the wheel, we have to look at the hidden costs of the modern space race, specifically the problem of metallic smog. As humanity prepares to launch tens of thousands of satellites for mega constellations like Starlink and Kuiper, we are facing a disposal problem. When a conventional satellite made of aluminum, titanium, and magnesium reaches the end of its life, it is deorbited. It plunges into the atmosphere and friction incinerates it. For decades, we thought of this as a clean disposal method. The satellite vanishes, and the risk of a collision in orbit is removed. But matter does not just disappear. It changes state. When aluminum burns in the upper atmosphere, it releases aluminum oxide, or alumina, particles. These particles are highly reflective and chemically reactive. Recent studies suggest that as we burn up more and more metal satellites, the accumulation of this metallic ash in the stratosphere could begin to reflect sunlight, altering Earth's thermal balance and potentially damaging the fragile ozone layer. This is the specific problem LignoSat was born to solve. Wood is organic. When a wooden satellite re-enters the atmosphere, it does not leave behind a cloud of metallic micropollutants. It burns cleanly, converting primarily into water vapor and carbon dioxide. It is arguably the ultimate leave-no-trace technology for the orbital age. But this brings us to the obvious engineering question. How can wood, a material we associate on Earth with rot, warping, and fire, possibly survive the vacuum of space? The phrase vacuum-resistant wood sounds like a contradiction. However, the engineering secret lies in understanding exactly why wood degrades. On Earth, rot is caused by bacteria and fungi, both of which require oxygen and moisture to survive. Fire also requires oxygen. Warping is caused by fluctuating moisture levels in the air. In the vacuum of space, none of these enemies exist. Space is an anaerobic environment. Without oxygen, wood simply cannot burn or rot. It is actually more durable in space than it is on Earth. While metal satellites suffer from atomic oxygen erosion, where single oxygen atoms in the upper atmosphere strip away material, wood's complex lignin and cellulose structure has proven surprisingly resilient to this specific threat. Then there is the issue of temperature. A satellite in orbit experiences wild thermal fluctuations, swinging from negative 100 degrees Celsius in the Earth's shadow to positive 100 degrees Celsius in direct sunlight, cycling every 90 minutes. Metals expand and contract significantly under these shifts. This thermal expansion requires engineers to design complex joints and thermal management systems to prevent structural failure. Wood, however, is a natural composite material. Its cellular structure, which evolved to support trees against wind and gravity, provides inherent thermal stability. The team at Kyoto University did not just pick any wood. They spent years testing different species. In 2022, they attached samples of magnolia, cherry, and birch to the exterior of the International Space Station for a 10-month exposure test. The results were stunning. After nearly a year of exposure to cosmic rays, the vacuum, and intense solar radiation, the wood samples showed no decomposition, no deformation, and no surface damage. Hinoki, or Japanese magnolia, emerged as the clear winner. It is native to Japan and prized for its uniform texture and high-dimensional stability. This is the same wood used for the saya, or scabbard, of a katana blade. It is chosen for swords because it does not warp or crack, ensuring the blade can always be drawn smoothly. In space, that same stability is what protects the satellite's delicate internal electronics. Perhaps the most fascinating aspect of LignoSat is how it is put together. You will not find high-strength epoxy or titanium bolts holding this chassis together. The engineering team realized that using metal fasteners would introduce weak points. Metal expands at a different rate than wood. If you screwed a metal bolt into a wooden chassis, the thermal expansion cycles in orbit would eventually cause the wood to crack around the screw. To solve this, the team turned to sashimono, the traditional Japanese art of joinery. Using complex, interlocking joints, specifically the blind miter dovetail joint, the craftsmen at Sumitomo Forestry built the chassis entirely out of wood. The pieces lock together with geometric precision, allowing the structure to shift slightly with thermal changes without cracking or breaking. It is a fusion of 1,000-year-old carpentry and 21st-century aerospace engineering. Beyond sustainability, using wood offers a massive tactical advantage for satellite designers: radio transparency. Metal satellites act as Faraday cages. If you put an antenna inside a metal box, the signal cannot get out. This means satellites must have antennas deployed on the outside, which adds mechanical complexity and risk. If the antenna fails to unfold, the mission is lost. Because wood allows radio waves to pass right through it, LignoSat can house its antennas inside the chassis. This simplifies the design, reduces the number of moving parts, and creates a sleek exterior that is less prone to snagging on debris. So how is the mission going? LignoSat was deployed from the International Space Station's Kibo module on December 9, 2024. The physical deployment was a success. Orbital tracking data from the U.S. Department of Defense confirmed the satellite was intact and tumbling through orbit as planned. However, the mission has faced a hurdle typical of experimental engineering. Following deployment, the ground team at Kyoto University reported difficulty in establishing a data link with the satellite. As of early 2025, the team is investigating potential causes, ranging from a failure in the battery activation switches to a software boot-up error. While this silence is a setback for the data collection phase, the primary engineering milestone has already been achieved: structural survival. LignoSat has proven that a wooden box, held together by friction and geometry, can survive the violent vibrations of a rocket launch and the vacuum of orbit without shattering. This mission is likely just the opening chapter. Professor Takao Doi, the former astronaut leading the project, has a vision that extends far beyond low Earth orbit. If wood can survive the vacuum of space, it becomes a candidate for building habitats on the Moon and Mars. Wood is rich in hydrogen atoms, found in the cellulose and water bound in the cells. This makes it an effective shield against space radiation, potentially better than aluminum for protecting human occupants. Furthermore, on Mars, we cannot mine aluminum easily, but we could eventually grow forests in domed biospheres. Professor Doi envisions a future where forestry is a key component of space colonization, allowing settlers to grow their own building materials. LignoSat is a reminder that innovation is not always about inventing new materials. Sometimes, it is about seeing old ones with new eyes. By engineering a vacuum-resistant spacecraft from the same material used to sheath samurai swords, Kyoto University has opened a door to a cleaner, more sustainable future in orbit. Whether LignoSat eventually phones home or remains a silent traveler, it has already delivered its message. The future of spaceflight might be grown, not mined. Thanks for listening to G Fun Facts Online.